Since ancient times, mankind has gazed at the stars, pondering the mysteries within our reach. What lies beyond the boundary of the observable universe? What secrets are hidden in the vast space of space? These questions have fueled our curiosity for centuries. Today, the James Webb Space Telescope, JWST, revealed something extraordinary, something that could change our understanding of physics and the universe itself. Join us as we embark on a journey to the farthest reaches of space to discover JWST's monumental discoveries. If you are fascinated by the wonders of the universe, subscribe to our channel, like this video, and turn on the alarm clock to stay updated with the latest cosmic revelations. Humanity has gazed up into the night sky for millennia, its collective curiosity piqued by the twinkling lights of distant stars and galaxies. What is beyond what we know? What lies at the edge of our universe? These fascinating and puzzling questions have guided scientific research for centuries. In a groundbreaking development, the James Webb Space Telescope, JWST, recently discovered something huge and terrifying in the farthest reaches of space, a discovery that could change our understanding of physics. But what exactly did JWST find at the edge of the universe? Why are scientists so excited? Let's dive into the heart of this monumental discovery. Albert Einstein's theory of gravity, proposed in 1916, changed Newton's earlier theories. Einstein's equations suggested that the universe could not remain static. It had to either expand or shrink. This pioneering idea was supported by observations made by the astronomer Edwin Hubble in 1929. He observed that galaxies move away from each other, which is a sign of the expansion of the universe after the Big Bang. This constant expansion can be easily explained by Einstein's theory, which allows for a universe that stretches without limit or curls back like the surface of a higher dimensional sphere. Some argue that the universe has an advantage because it was created in the Big Bang about 13.8 billion years ago. But what lies beyond that edge remains one of the great mysteries of modern cosmology. The universe is divided into observable and unobservable. The observable universe is all that we can see thanks to the radiation that our instruments can detect, and its boundary is marked by the cosmic microwave background, CMB, a remnant from about 13.8 billion years ago, when the universe was opaque, like a thick fog. However, some experts believe that gravitational waves and neutrinos come from even more distant places. Unfortunately, our current technology cannot guarantee this. To better understand the universe, cosmologists argue that what we observe is only a small part of a much larger reality. Discovering galaxies like at 2744_Y1 at the far edge of the observable universe helps us understand this larger reality. Although the light from this galaxy took 13 billion years to reach us, this gives a glimpse of its state 650 million years after the Big Bang. The discovery of A2744_Y1 was made in collaboration with the Spitzer, Chandra, and Hubble telescopes, each capturing different parts of the electromagnetic spectrum. By combining their data, astronomers can spot galaxies that are up to 100 times farther away than a single telescope. The work was led by astronomers from the Institute of Astrophysics of the Canary Islands and the University of La Laguna, who used the Hubble Space Telescope to measure the distance of the galaxy and stellar content with the Spitzer instruments. They also used the gravitational lensing technique, which magnifies distant galaxies using the gravitational pull of nearby galaxies. Despite its small size compared to the Milky Way, A2744_Y1 has a star formation rate 10 times higher. Its redshift, which shows how much its light has been stretched to longer and redder wavelengths as the universe expands, is 8. This means that the light we see today has been traveling through the ever-expanding universe for billions of years. Before the discovery of A2744_Y1, the most distant known galaxy had a redshift of more than 7. But now astronomers have detected something even more distant, a supernova called DS16C2 The supernova discovered by international astronomers in 2016 represents one of the most massive explosions in the universe. Its light was born about 10.5 billion years ago and has traveled through space for most of the history of the universe. Unlike typical supernovae, DS16C2 is a dark supernova that emits little visible light and is detected mainly by infrared radiation. Powerful telescopes such as the Magellan Telescope and the Keck Observatory were used to discover DS16C2. It took more than 5 years and more than 500 nights to detect this distant supernova. The effort was enormous, but the rewards are significant because the study of such distant supernovae helps scientists understand the evolution of the universe and the causes of these massive cosmic explosions. The explosion of a supernova like DS16C2NM releases enormous amounts of energy, mostly in the form of neutrinos and photons, creating a shock wave that travels outward at thousands of kilometers per second. This shock wave heats the surrounding gas and dust and emits visible radiation at different wavelengths. In addition, the explosion produces heavy elements such as iron, gold, and platinum, which are essential for the formation and life of the planet. These elements are scattered throughout the galaxy, enriching the interstellar medium and providing the raw material for future stars and planets. By analyzing the ultraviolet light emitted by a superluminous supernova, SLSN, scientists can determine the amount and temperature of matter produced during the explosion. This information is crucial to understanding these events. Comparing DS16C2NM with Betelgeuse, a red supergiant expected to explode as a Type 2P supernova, highlights the differences between supernova types. DS16C2NM, a Type 2 supernova, was formed when a massive star ran out of nuclear fuel and collapsed, while Betelgeuse undergoes a less catastrophic Type 2P explosion. Now experts are looking for other distant supernovae that go beyond the limits of our knowledge. What lies beyond the boundary of the universe? The search for understanding forces us to confront fundamental questions about existence, the nature of reality, and the structure of space-time. Theoretical physicists and cosmologists grapple with hypotheses that extend beyond our cosmic horizon, wondering whether space-time stretches infinitely or warps to dimensions beyond our current understanding. This quest for knowledge drives the development of observational astronomy and pushes telescopes like JWST to probe deeper into cosmic history than ever before. Every discovery, whether it is the detection of distant galaxies or the observation of ancient supernovae, provides a glimpse into long-distant eras and important clues about the origin and evolution of the universe. The observable universe, which stretches as far as light has traveled since the Big Bang, spans billions of light years. However, beyond this observable horizon lies the unobservable universe, regions where light has yet to reach us due to the expanding fabric of space-time. The cosmic microwave background, CMB, the dim glow of the universe, provides insight into the universe's infancy, revealing its early conditions and forming the background against which galaxies and cosmic structures form.
JWST, poised to follow the Hubble Space Telescope, promises to change our understanding of the early universe and its evolution. Equipped with advanced infrared detectors, JWST probes deeper into space and time, capturing light from the first galaxies that formed shortly after the Big Bang. This unprecedented ability allows astronomers to study the cosmic dawn, the period when the universe went from a dark, opaque state to being illuminated by the glow of the first stars and galaxies. To understand the origin of the universe, scientists study phenomena such as gravitational waves and neutrinos. These signals, generated by cataclysmic events such as colliding black holes or supernova explosions, open windows to the world's most extreme and energetic processes. While gravitational waves ripple through space-time itself, neutrinos, ghost particles with almost no mass, travel vast distances largely untouched by cosmic barriers. Detecting and interpreting these signals requires sophisticated instruments and international collaboration that pushes the boundaries of technological innovation and theoretical physics. Astronomers use various observational techniques to study the distant parts of the universe. The gravitational lensing effect predicted by Einstein's theory of general relativity acts as a cosmic magnifying glass that bends and amplifies the light of distant galaxies. This effect allows astronomers to study galaxies and cosmic structures that would otherwise be too dim or distant for direct observation. Together with terrestrial observatories and space telescopes such as the European Southern Observatory's Very Large Telescope, VLT, and the Atacama Large Millimeter/Submillimeter Array, ALMA. These tools allow astronomers to probe deeper into the mysteries of the universe. The study of distant galaxies provides insights into cosmic evolution and structure formation on the largest scales. By observing galaxies at different distances and in different epochs, astronomers can trace the evolution of stars, gas, and dark matter over billions of years. Galaxies like A2744_Y1 discovered by the Hubble Space Telescope and studied with follow-up observations from ground-based telescopes offer a glimpse into the early universe. These observations indicate that galaxies are in their infancy, with rapid star formation and conditions that may resemble those of the early universe. The discovery of distant supernovae like DS16C2 and M sheds light on the explosive deaths of massive stars and their impact on cosmic evolution. Supernovae are the most energetic events in the universe, releasing enormous amounts of energy and synthesizing heavy elements essential for the formation of the planet and life as we know it.